Welcome everyone. In this lesson, we're going to see how to solve problems involving exponential growth and decay. So we're going to start with exponential growth. And kind of our motivating example here is a bacteria culture that doubles in size each day. So we're going to assume initially one bacterium is present, and we're going to see what happens as this population of bacteria grows over time. And what we're going to do to kind of illustrate this point is we're going to determine the size of the bacteria population after 3 days. All right, so let's kind of draw a little picture here just to see what's going on. And we're going to look at how many bacteria there are when we start. So T0. Then after 1 day, and then after 2 days, and then on our 3rd day. And we're just going to kind of count them up. So let's suppose that we have, on day 0, we have our 1 bacteria. There it is. There's our 1 bacterium there. All right, so we have 1. Now after 1 day goes by, how many bacteria are there going to be? Well, the number of bacteria doubles each day. So after 1 day goes by, this bacteria essentially is going to become 2. So the population doubled. We went from 1 bacteria to 2 bacteria. All right, so that's after 1 day. Now another day goes by. So we're on day 2. How many bacteria are there going to be? Well, this bacteria here is going to split. It's going to double. And then this bacteria here is also going to split. So we're going to get a doubling from here. So what happens is from this bacteria, we're going to have 2. And then from this bacteria, we're going to have 2 more. All right, so now we have 4. We started with 1, now after 1 day we had 2, and now we have 4, and then we're going to let 1 more day go by. So we'll be on day 3. And what's going to happen is each of these 4 bacteria is going to split. And so for each of these, we're going to end up with 2 more. So how is this going to look? Well, from this first one down here, we're going to have 2. From this one right here, we're going to have 2. And let's and then from this one right here, this one's going to split, so we're going to have 2 more. And then finally, this last one's going to split, so we'll have 2 more from there. So if you count it up, how many are we going to have? We have 2, 4, 6, 8. So there's going to be 8 bacteria on day 3. So if we start with 1 bacteria and the population is doubling in size each day, what happens is we go up by powers of 2. So we can think of, the way we can think of this is we can think of our population on day 0 as being 2 raised to the 0. And we can think of our population on day 1 as being 2 raised to the power 1. And we can think of our population on, well, not quite 2 raised to the power 1. It would be whatever our starting population is times 2 raised to the 1. And then on day 2, it would be whatever our starting population was times 2 squared, so 4. And then on day 3, it would be whatever our starting population was in general times 2 cubed. So each day that goes by, we're multiplying our starting population by a power of 2. And what we end up when we kind of consecutively multiply by powers of 2 like this, what we get is an exponential growth curve. And that's what we're seeing here. This is an exponential curve. With positive growth, so it's going up. Eventually we're going to see examples where we might have decay, and it's going to look similar, but there's a separate graph that we'll consider for that. So this is going to be positive growth. And if we plot our population on here, on day 0, we start with 1. So that's what our initial population was for this little motivating example. And then after 1 day, we had 2. And then after 2 days, we had 4. And then on day 3, we had 8. And you can see it fits this exponential growth curve here, our population does. And so what we're doing is essentially we're multiplying here by powers of 2. So what we're seeing is this exponential growth. And so we can generalize this behavior, and that's what we're going to look at. So we say that a population or quantity is growing exponentially if at every time t, the rate of increase of that population is proportional to the size of the population. And that's what we're seeing in that motivating example. So what is actually happening here with exponential growth? Well, the rate of increase, the rate that our population has increased, that's the derivative, is proportional to the size of our population. So that's what we're seeing here. The derivative, p prime, represents the rate of increase. And our function p represents the size of our population. So the derivative is a rate of change, so it's how much our population is growing. And then our function p just represents the size of our population. And so what this is saying is that something is growing exponentially if at every time t, the derivative, p prime of t, divided by p of t is equal to some constant k. And that's what it means to be proportional. So that's what this equation means to be proportional. If you have two different quantities and they're proportional to each other, well, if you divide one by the other, it's always equal to a fixed constant, in this case k. All right, so if we rewrite this equation, though, so multiply both sides by the function p of t, this is another way to think of proportionality. What we get here, though, is a differential equation. So we have this unknown population function, p of t. We don't know what the population function is. We just know that it satisfies this differential equation. It says the derivative of p must be equal to some constant k times the original function, p. So this is a differential equation. It has an unknown function, and it turns out that the solution of this equation is right here. So this is a whole big, differential equations is a whole big field of study. This is just one little example of what a differential equation is. It relates the derivative of a function with the function itself. And we don't know what that function is. So it turns out, though, that the solution for this differential equation is our exponential growth function. So p of t is equal to p of 0 times e raised to the power kt. So it's this exponential function. And we probably would have guessed it just by looking at this curve over here. This is an exponential curve. All right, so in this equation, in this function, P of t represents the population, the size of the population at time t. And in order to really fully know what this function is, we need to know two things. We need to know our starting population, and that's what P0 is here. P0 is our initial population. So it's our population at time t equals 0. So another way to think of this with function notation is just our function, our population function evaluated at time 0. So we kind of abbreviate that with this P sub 0 notation. So we need to know that, and we also need to know K. So K there is a constant, and we call that, a lot of times we call that our growth constant. And for growth, we're assuming here that K is positive. If K is negative, then we have decay, and we'll consider that in a separate example. So right now we're just looking at exponential growth, where that constant term in our exponential function is positive. So another format for this is, so this is more of a differential equations approach to this formula, but a kind of an alternative form equally valid. So this differential equation form uses the natural exponential function, e raised to a power. Another form involves exponential function, but with base 2. And so we can also think of this as the starting population, P0, times 2 raised to the power t over what we're going to call capital T. Now this form kind of agrees with what we were seeing in our motivating example here, where the population was going up by powers of 2. So that's, sometimes this alternative form is a little bit easier to conceptualize, because we have our initial population and then we're just multiplying by powers of 2. So you can show that these two are actually equivalent. But what is this capital T? Capital T here in this alternative form is the time it takes to double. So, sometimes it's easier just to use this formula. Sometimes it's a little bit easier with calculations to use this formula. And you still need to know two things. So you need to know your initial size for both of these. And then for this one, you need to know what K is, the growth constant is. And for this alternative form, you need to know, well, how long does it take for your population to double? And so there is a relationship between K and this value capital T. And you can show that K is equal to the natural log of 2 divided by capital T. So you could try plugging this value in for K and then just using the property of E and natural log, and what you would see is that E and natural log would kind of cancel, and you would end up with this alternative form. So we have some options here on how we want to model exponential growth. We can either use our natural exponential function, which sometimes is nice because E is always pleasant to work with in calculus. but conceptually maybe this format's a little bit easier to visualize what's going on. All right, so we're going to look at a few examples where we apply these formulas. So we'll see you there.